Okay, I think it's time to begin with today's lecture. So it will be the last one before the exam, and some quick information about the exam. I think if you have already signed up by now, so you guys will do it here in Kalmar, but since we have a distance student, so the distance students, I will put more information on the course page for the distance students, but the process will be like on the specific time, the question paper or all the tasks for the examination for the distance student will be uploaded on the Moodle page. And since they will be doing it from the home, so the level of difficulty will be almost the same, but maybe some of the tasks could be different than those being done here in the campus exam. And then the distance students, of course, if you're doing it from home, unlike those you are doing it in the campus where you don't have an access to the computer, but those guys who are doing it home, they can use the IDEs and the computers to solve the problem and the assignments tasks. And there might be some tasks which requires to provide the Java source code. So then in that case, the distance students have to upload the Java source files, just like you did it for your assignments. And there might be other tasks like non-programming tasks requiring some diagrams or some paperwork. And for that, we don't require you to use something like a word processor or LaTeX or PDF. So you can simply use paper and use your cell phone to take a good quality of picture that can be viewable and understandable, and then upload it. And don't forget to upload it before the time ends on, because both, I think, for both kind of students, the time will be the same, like 5 hours. Okay, so that's some information about the exam, and today we will be talking about the last part of this course, which is about formal languages, regular expressions, and the different methods that we can use to recognize these languages and the constructs. So for example, if you want to define as a part of being a computer scientist, and if in the future there might be some courses that require you to write a code that can be used as a compiler to recognize strings or maybe statements in a language. So you will get a quick introduction. Of course, this lecture doesn't provide you all the details, but you will get some basic information about like what a context-free grammar is and what a parser is, and how can you write some basic code to recognize different constructs in some language. Okay, and also related to this part, you will get a fourth assignment, the final one, hopefully by the evening today it will be uploaded. Okay, so and before that, if you have a question, of course, anything that regarding exams or whatever, you can ask maybe during the lecture or after that. So these are the things that we will be talking about today. So starting with the basic concept is like a language. So it doesn't matter if it's like a programming language or if it's like any ordinary language. But since we are concerned more about the programming languages, so if somebody asks you like, how do you define a programming language? So for example, if you have to define a language like Java, so how will you start? What should be your approach? Since now you have been working with the Java, so what comes if you have to define a language of your own? So what should be the first things that you would like to? Words. Yeah. Okay. Yeah, right. I mean, and if you talk about Java, maybe like keywords or if, while, and you need to define. And when we say that defining a word, you need to, I mean, usually in a language we have like two things. We have a syntax, and then we have a semantics. And the syntax is like how this word looks like. It's more like a visual form. And semantics is what does it actually means, what actions are behind that word. So for example, if you write a for, so how should you write a for? Should you, after the for, should there be a semicolon or like a parenthesis? Do you need to define, assign some value, or maybe identifier and increment, decrement? And so that's like a syntax. And then also like the semantics is like what should it do, okay? So that's one way you can define, as you said, that you can define the words. And a more maybe detailed approach could be like, okay, if you are talking about a language, you can identify all possible. One way is like you start defining like a basic word, and then you start combining those words, and all the possible combination of words or sentences in a language, which seems to be quite impossible, because you can combine and you can come up with as many. If you have like maybe even 20 words in a language, you can combine them in a different ways, and you can get a lot of different sentences. The same holds for Java. I mean, one way could be like, okay, you can define all the correct. If you have defined all the correct programs in Java, maybe you have defined something, but then it's quite infinite. I mean, there could be like, yeah, more than the population on this universe. And it's another approach could be like, okay, instead of defining the right or the correct Java program, we identify what is wrong, what is incorrect, what is not acceptable. But then it's also like something that's quite hard to do. And other approaches could be like, as you said, that we can start you can either start with the identifiers and the words. And also, I mean, you can start, if we consider Java, so we see that every program in Java is like a class definition. So you can start maybe with the class declaration, so how a class looks like. And then you can define, once you are done with the class, maybe you can go one step down, because in the class we said that we have like methods, and we have like the fields, attributes declaration. And then you can define the methods, and once you have done with the methods, maybe in the methods you have different statements. So you need to define the statements, and once you are done with the statements, maybe you have to define like different kinds of statements, like is it an assignment statement, iterative statements, control statements, okay? So, and then, so for all these kind of approaches, you need to define these things, okay? And often when we talk about language specification or language definition, so we come up with some kind of rules, okay? So, for example, and these rules are in terms of language terminology, we call them like a grammar. So, for example, you have a grammar rules for the Swedish language and the English natural languages. So, in what order you can combine the words, whether it should start, a sentence should start with the noun, or and then it should be, there should be like a verb, and then it should followed by adjective or prepositions and these kind of things. So, similarly, to define the programming languages, we have different techniques. We have different methods like regular expressions and context-free language, context-free grammars. And in those language definitions, so for example, if we look at the Java language specifications, so maybe, so I just Google this Java 12 language specification. So, and then if we open this one, let's see, the internet is working, yeah. Okay, and then if we see the latest one, okay, so, and maybe if we have something like a class declaration, so you have something like this for the class declaration in the Java specification, where you have defined like, okay, it should, like for a normal class declaration, of course, I mean, in Java, they distinguish between an ordinary class declaration, and then we have like enum types, because both are like type used for declare a user-defined data types. And if it's like a ordinary normal class declaration, then it should start with a class modifier, and then there should be a class keyword, and then the identifier for the class, like class name student, and then it should have like maybe type parameters. For example, if it's like a generic class, and then you could have like a super class, yeah, and super interface, and then you can have a class body. And if it's like a class body, you can also have a declaration for the class body that it should start with the braces, curly braces, and then should you have a class body declaration. And in the class body declaration, you should have class member declaration and instance. So you have like a number of different recursive statements you define like one by one. Okay. So similarly, if you see here, we say that a program, which is a Java program, is composed of maybe one or more than one class declaration. And what is class declaration? That it should start with the keyword public, let's say, and then the keyword class, and then identifier, and then the left bracket, and then you can have either in the class declaration you can have a field declarations, or you can have a method declarations. Okay. And then in the end you have a right brackets like to close the class definition. And this star, we use something that can be repeated more than once. So it means like a class can have 0 or more than one field declarations. And then you have method declaration statements. And this is more like a context-free grammar, and we will see how the context-free grammar looks like. And often for like low-level details like identifier, then because this is here we are describing more like a high-level constructs like a class, and then the methods and the fields and the statements. But when it comes to the like the keywords and the identifiers and the variables, so we often use regular expressions. Okay. And I don't know if you are already have used or are familiar with the regular expressions or not. So these are like patterns. Using the regular expressions, you define a patterns to search the words in a string or something like that. So, and we will see how you can build your own regular expressions, and then you can use those regular expressions to see whether this word or the sequence of characters belongs to a particular language or not. Okay. So, for example, if the language we have is like a Pascal, and or even if you consider the Java, and in the Java we have some rules for the identifier definition. So, for example, we say that an identifier can contain all the letters from A to Z, and then it can also contain also the digits 0 to 9. But the digits cannot, identifier cannot start with a digit. The starting letter in an identifier, for example, a variable name, it must be either alphabetic character A to Z, or it may be a special two special letters like underscore and dollar sign. But it cannot start with the digit 0, 9. And similarly, if we talk here about Pascal, so the Pascal identifier rule is that it should start with a letter, and the letter could be like either small capital or small A to Z. And after the letter, for example, if you are starting with the A, and then it could either contain another letter or it can contain a digit. And this digits means, and if you want to say like, because after, I mean, the variable name, a legal variable name, it could be like only just a single letter, like integer A. That's fine. But it could also contain more than one letter, like integer marks, integer name, string name, string marks. So in that case, it means that if you see the letter, it means like only one of them. But if you want to see that a letter can come more than once, then you have to use this star notation. Okay, and the star notation means like this part, because we have a star on both letter and digit. So it means like this part can come 0 or more than once. So it's like a multiplicity notation. So if we ask like what is a language in computer science, so just like an ordinary language, the basic parts in any language are like alphabets, like the symbols. Okay, so for example, when we learn Swedish language, we start with like all the Swedish basic characters, alphabets. And in terms of language, we often call them, every letter we call like is a symbol. And the set of all the symbols in a language is called like an alphabet. And when we combine those all the different symbols from the alphabet, we get something like sentences or strings that we usually call words as well. Okay, so we can simply say that the three important things in a formal language definition is that there must be some symbols, alphabet, and then the strings. And the strings, you can consider them as the statements as well, okay, or the sentences. So for example, here we have like a language which is that has only two alphabets, A and B, okay. However, even if we have like two symbols, A and B, we can combine them. These two symbols can be combined in infinite number of ways. We can start with the A, and then keep on adding it, okay. So, and also if you consider another binary language, so we know that if it's like a binary, so it's only like a 0 and 1. So it means the language defined in the binary language, all the instructions are written in the form of 0 and 1s, okay. So, and then there are some basic concepts. So for example, a length of a word, we denote it using this notation. And also if it's like an empty string, an empty string is, you can understand it like a string without any symbols in it, okay. So it's like just like when we count about the numbers, so it's like one number, but we also have like a 0 that shows like nothing. So in terms of like if you have alphabetic symbols, then the empty string means like there are no symbols. And then we also have a concept of closure of an alphabet, and the closure is like the possible all the different strings in a language. So it's like an infinite set of all strings over the alphabet that you have. So for example, as I said, that if you have an alphabet composed of only two symbols, the closure is all the possible combinations of the different strings that can be formed by combining A and B, okay. But if you have to define more formally, a formal language is like L over this alphabet denoted by the sigma is a well-defined subset of this closure on the alphabet, okay. Obviously, I mean in a language it must be some limitations, otherwise it can be like an infinite language definition. And then there are some, when we say that language definitions, so we have some common problems. So the first problem is like the definition itself, because why it's a problem? Because we can have infinite number of strings or sequences. As I said, that in Java you can have infinite number of Java programs. And then also like recognition is also a problem when it comes to the languages. So for example, if you have defined a language, and then if somebody writes a program in that language, you need to recognize, to validate whether this program, is it a valid Java program or not. So for example, if you want if you have written an instruction, and if you have written a program, before executing that instruction, you must have to validate it. And then we also have a problem related to the recognition with the noun of parsing. So it's like so for example, the parsing, we call it if you have a language and then you want to validate it, usually when you use the compiler, and in the compiler you have this parsing process, and in the parsing process you transform your program into some smaller units that we call lexemes or the lexical tokens. And the tokens usually to generate the tokens and to validate whether these tokens are in a valid combination, you use the parsing techniques. We will see these things in more details as we proceed. One of the simple the languages, we have like different categories of the languages. Like we have a formal languages, and we also have like context-free languages, and then we have regular languages. These are the languages that are defined using the regular expressions. And the regular expressions, they are like kind of like the simplest languages. And why they are the simplest languages? Because in the regular languages, we only have these possible basic constructs. And the constructs means, so for example, if you have an alphabet A and B, so we can use this alternative construct, A or B, and concatenations. It's like more A followed by B, and then we have this multiplicity, so star symbol, so which shows that A can be, if you have written an A star, it means like A can be written 0 or more than once. Okay. However, as you have seen in our mathematics, because in the mathematics you also have rules. It's like a language that you use to define different expressions. Okay, like arithmetic expressions. And in the arithmetic operations, you have like operators and the operands. So same like here, A and B, they are like more like operands, and the constructs we have, it's more or less like operators. And but for the arithmetic operators, we have the precedence. So for example, multiplication and divisions are usually performed before addition and subtraction. So same like if we have these constructs together in one regular expression, so which one will be evaluated first? So, and for this we have a rules, and the rule says that the star operator, it will always have a higher precedence, and then concatenation has a second precedence, and the lowest precedence goes to this OR construct. And we see, if we see some example, maybe it will become more easier that how can we use regular expressions. Okay, so here we have a regular expression, and we usually denote the regular expression with the smallest r symbol, and we say that, and all these regular expressions, they are defined on a language that has only two symbols in it, A and B. So it means that we cannot use any other symbols for the regular expressions that can be used to define the language on that alphabet. And it says that this R defines the language, which should always start with the letter R, A and B, and after that it could be either an empty string, or it could be a sequence of B and A, or it could be the sequence of A and B. So from this regular expression, how many words can we get? Can we get infinite number of words, or can we get just only limited? Yeah, we can get in what combinations, because this says R, it means like we can pick any of these threes. Okay, so if we pick empty string and combine this, because this is like a concatenation, and combine this with A and B, we get this word AB. And then instead of this, if we pick this, we get another word, which is ABBA. And if we pick instead of these, we get AB, we get this. So it means that through this regular expression defines the language on the alphabet A and B, and in that language we have only 3 words. That's quite a limited language. So it's not a infinite, it's a finite language. So, and then we have another regular expression, and it says like it starts with a B, and then the A can be present either 0 or any number of times. So when we say that any number of times, it means that we can get an infinite number of words. But in this language, all the words must start with letter B. If you write a word or a string that starts with the letter A, then that string is not part of this language, the language defined by this regular expression. So, for example, AB is part of this language defined by this regular expression, but it cannot be part of this language. Similarly, we have another regular expression where we say that both AA or BB, I mean, whenever you use an AA, it should be used as a combine. So it means that you cannot use A and then followed by B, because it says only two combination of the symbols A and B, which are like double A and double B. Okay, so it defines the infinite language. Why? Because we have this multiplicity notation. So, and from this language we get all these different number of possible words. Do you understand now how can we use regular expressions? So basically, in the regular expression we have three constructs: or, concatenation, and multiplicity. Now maybe we can look at so here is some simple exercise just to see did you really understand the concept of regular expressions or not. So here we have a set of symbols, the alphabet, and the alphabet is again composed of only two symbols, A and B. And I would like you to define a language. In the first language, it should have strings, and the length of those strings or the words must be an even number. So it cannot contain strings of length odd numbers. So for example, it can have either AA, AB. Is it 0 is an even number or not? Is it 0 is even or odd? I think it's even. 0 is treated as even. Okay, so it means like empty string is also okay. And then we have another language, number 2, and for that language the requirement is the length of the strings must be a odd number. It cannot be, so it means like when we say the odd number, it means like the empty string is not allowed over here. Okay, it must contain either A or B or maybe more than that. So can you help me to define this language? Let's see if the whiteboard thing works over here or not. Yes, almost, yeah. So we have the alphabet. And in the first, we have strings of odd length. So R1 and R2, we require that strings of even and odd length. Can you give it a try?
In parentheses.
Sorry?
So within parentheses having the empty or AA or
Empty or
AA,
AA.
AB, BB, or like all the different and having those multiplied.
And having those multiplied like this, or you mean like here, like this?
Or no, afterwards, since they always will be either 0 or.
You mean?
I might be wrong.
No. I mean, I just want to give it a try. So.
Yeah, but by having that they always have to be concatenated to 2, they will always be even.
Yes.
No matter how many times they will be added together.
So let's stay. Okay. Yeah. Can you give me some words of even? I mean, any combination of words. AA. It has a length even. Now you can test with this. Can we get this word from this? Yes, we get it from here. If we put this one, so we get this one. Okay. Any other combination? Any other word? 4A. 4A. Like this? Okay. So the language says that because this star is on all, so it means like this part also has a star, so we can use it more than once. So if we use it 2 times, we get this one. Fine. Sorry? 3A's, yes. If I pick it this time, okay, I get 2. If I pick this one, okay, I don't get anything, but then I will not get the 3rd A. So that's not possible. Fine. So I think whatever combination of the words you get, because, and the only thing is that since we say that the star means like you can omit all those words, so it's already, if you use a star, you don't really need the empty string, because star means like you can skip them 0 number of times, so then it's like empty by itself. Okay, I think yeah. So what you need to do is like you identify the basic combinations, because we have only 2 words, and since I cannot use A alone, because then its length will be odd. So I must use it A with some other symbol, and the other symbols are only 2. Other symbols are, if I have taken A, the other symbol that I can combine with this one, and they are like A itself or B. Okay, so AA and AB, and then if I took the other part, the other symbols are again the same, like BA and BB. So you basically identified all the basic combinations, and then since we have, like we said that the length can be even, so it means like even could be like 2, 4, yeah, 6, 8, so on. So it means that these can be combined. Even if we combine them any number of times, we will end up with an even length. Okay. So we are done with the first language. So we have defined regular expression, and you might get a similar kind of question in exam, by the way. So it's could be a good practice to do it over here. So and then if we have a second language, and in the second language we say that all strings the same alphabet, but this time the length should be the odd one. Could someone give me the regular expression for this language?
A.
With the A? Sorry? A? The basic is A, yeah?
B.
Together with A, or?
Separate.
You mean R or?
Okay.
Because these are the constructs.
Okay.
Because if I write like this B, then it's like a concatenation. I mean, if you want B as a separate one, then you can put this one. Then it's like another case. If you want B as a single one, as you said that only A, and if you want only B, then you should use alternative form like R. So as I said that A and B. Okay, and then
BBA.
BB, you mean BBA? But let's see if we see. I mean, it could be even AA, but you don't get it here.
It might be like first one, but adding A or B in front of it.
Exactly. Because odd is if you add one, just one to any even number, you get an odd number by it. Okay? So if you have defined it for the even numbers, for the even length, and before that, if you add just one A or B, you will get a string of all the different possible words with the language A and B, where the length of strings will be odd number instead of even numbers. Okay? So that was kind of not so complex, I guess. Then we have a second exercise. And in the second exercise, this time we are using more more symbols. So our alphabet this time for the second language is has symbols minus, 0, and D. And where the D is representing the digits from 1, 2, 3 up to 9. Okay? And the requirement for that language is that write a regular expression R such that R represents all integers. Okay? So the language that is required is R1 should represent all positive integers or no, all integers. Okay. And the integers means it could be positive integer or it could also be a negative integer. However, there is some other details given that 0 is neither positive nor negative. So you can, the language should not allow minus 0 because minus 0 is not an integer. And also it should not allow the integers with the leading zeros like 0, 5 or maybe 0, 0, 5. So these are things that are not, that should not be accepted in your regular expression. So can we write a regular expression for this language? Can we, because this is written in like more like a natural language. But if we have to define this, if we have to write this in using a natural language, regular expression, can we do that? Maybe try to think about, like as I said, I think it was 1 or 2 lectures ago when we talk about like when you have a problem. So instead of solving the general problem, maybe start with the instances of the problem. So maybe we can start here with the problem instances. So we can take some words that belong to this language and try to define a regular expression for that. So like for example, what can be the different words, basic cases? What can be the basic cases for these integers languages?
-1.
Yeah, -1, 0, 1, 2. Yeah, so we can say like single digits. Okay, 1 to 9. These are like some, and then if we combine these 1 1 1 2 113, we get new words. And we can also use, when we say like 1 1, we can also use 0 at the second position, but not at the leading position, 1 0. Okay. So it means that if I consider this case 1 to 9, this case is given over here. Okay. If I write my regular expression, if I take this part d, I get all these integers. This d gives me only these things. And then if I have to define this one, 1 0, can 10 be defined by this? No. So what I need after that? After that, it means like after the digit, for this, I need a, and for all these 1, 2, 3, up to 9, I need again d. And we also know that this 1 1, it could be like 1 1 again, or it could also be like after 1, it could also be like 0 1. So it means that this part can come and when we know that this 0 and d can come many number of times, can I remove this d?
No.
Why? Then it can also start with the 0. Exactly. So we need d always over here, because if we remove the d at this position, then we allow the language to accept the word starting with the 0. So now we have solved these cases 1 to 9, and what is left now? Negative is left, okay, because this is defining only the positive integers. And for the negative, we have this symbol, and so how can we put negative over here? We need to concatenate negative, okay? So we cannot use the alternative form. If I put negative over here, then it will always gives me a negative number. So it means that then I have to use the R operator. Sometimes for negative, I need this negative symbol only for the negative integers and not for the all integers. So minus R, if I use the empty string, then I can choose between. If I need a positive integer, then from here I will choose empty string. Have we covered all the cases now?
Didn't get that last part. Can't that be a 0 then? Or
Which one?
the first one on the left, the minus and then the empty string.
Yeah, because if you don't use the empty string over here, okay, then you are saying that always you start with the minus sign, okay, and in that case, if you start with this one, you pick a minus and then you can put d, and d is like 1 2 3 minus 1, and then you can use 0 or maybe more 2 3 4. So by putting minus, then this regular expression will only generate negative integers. It will not be possible to generate positive integers. And how can we generate positive integers? By writing an expression where minus should not be used always, but it should only be used in some cases. And how can we choose? We can choose using this R notation in the regular R operator. So if we should like put this, and why I need to put empty string over here? Because I have already defined the things that I need for the positive integers. So I don't need to, for the positive integers, I don't, of course, I mean, there is no plus symbol. If there is a plus symbol, then you can put the plus symbols, because then it will give you something like a positive integers. Do you understand now? We can take that later on if it's still a problem. So now my question is, have we covered everything that is needed now? What is left?
0.
We are missing 0.
Yeah.
Okay. So
If we take all that in parentheses and
maybe if we put,
Yeah.
because that's a basic case, so we don't. So 0, 0 can come alone. That's fine, but it should not come as a leading 0 in other integers, in other words in your language. Okay. So where we have a solution. First one we already have done for this, an even number, and we have all the combination, the basic one, and then we have a multiplicity notation, and then we also have the regular expression for the second language, where we have a similar like A, B, and then in the beginning we put A or B. And we also have a solution over here, which is almost something like we done over there. Yes, you have a question?
doesn't this accept like an empty string as the correct answer as well?
This one, you mean? It accepts what?
No.
We are talking about the integers.
Was
This expression accepts only the integers, and the integer mean like it could accept positive integers, negative integers, and 0.
I was neglecting that concatenation between the empty and the minus.
Okay.
D. That's
Uh-huh.
why I was kind of, couldn't you like take away the empty list and the minus or D concatenated to 0?
If you can you use the pen and write what you mean?
So like, this instead, wouldn't that be the same?
Minus, no.
Minus or
But then, because if you write it like this,
yeah,
then I can minus with this
yeah.
0, and then it will become minus 0.
Yeah, sure, yeah,
Okay.
yeah. That will do.
Okay, so we have seen a few examples for the regular expressions, and I told you that there are 3 basic constructs in the regular expression, which are like OR and concatenation, A dot B, and then we have this star. But in some books and in some online text, you find some other constructs like plus, and the plus means once or more. So if you want to have some symbol that should come at least once, it's like but you can also achieve it even if you don't have a plus. You can write it like this with the star. Before, if you put R once before the symbol that you have for the multiplicity notation, you will get the same thing. And if you want to use that it can come 0 or once, then you can also use question mark. But you can also put it like with the empty string. And also, if you have like we have the D, which was starting from 1 to 9, you can also have constructs like this 1 to 5 instead of writing all of them. And same like with the alphabets. So these are like some alternative ways. And here we have in the bottom again we have a regular expression for the identifiers in the Pascal language, and it says that it must start with the letter, and the letter means like any combination from A to Z, and after that it can have a digits. So we have now seen few examples of regular expressions, and how can we use regular expressions to define our languages, what is acceptable and what is not acceptable. And in order to recognize, if you have a string, and then if you want to test whether this string is a valid string for your language or not, the language that is defined by regular expression. So one approach is to use finite automata. Okay, and what is finite automata? These are like abstract machines that we can use to identify strings. And when we say that the machine is not like something real machine, it's like an abstract machine. And basically in that machine we have the nodes and edges, just like we have in the graph data structures. And in the in this DFA, we have some states as an initial states or the starting states from where we start, and then we also have some final states. Okay, and using this DFA, finite automata machine, if you have a regular expression, and then using that regular expression, you can define your finite automata, and then you can use that finite automata to test whether a word or string is a part of that language or not. And how can you do that? We will see in a short while. By using a finite automata, if you start from a start symbol and end up on the final stage, then it means that that word is a part of your language that is represented by a finite automata. But on the other hand, if you don't end up on the final state, it means then that string is not a part of your language. So for example, here we have this regular expression A or B, and then B, A comes many number of times, and then it ends with the B. And here we have this automata, and if we say here, it should start with the letter A or B. From the initial state is 0, and then we can start with either A, we have a path for the A, and we also have a path from the B. And after A and B, there must be the next symbol must be B. So after A or B, the next symbol we have is B over here. And after the B, we can have A many number of times. So it means like we have a loop on that state. And then it should end with the symbol B. So we have a symbol B, and that means we have come to the final state now. So if we see an example, maybe it will become more clear. Let's say, can you give me some word, any word which is just composed of any these two symbols, A, B, 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 or A, B, B, A? A, A, B. So we start with the A. So the word you given us with the 2A and then ending with the 2Bs. We get an A, and after the A, you again have a word symbol A. But from this, because when we start from the 0 state, initial state, we go to the state 1. But from after the state 1, we don't have any path that leads with the letter A. It means we cannot go to any state further. So that word is not part of the regular expression defined by this DFA.
How about if you end with a B? If you have like A, B, A, B.
A, B,
A, B,
A,
B,
B, yes.
then what happens?
Again, you will not be able to end up because your string has not finished yet. You find the B, but there was one more left.
Yes.
So it's not a part of that language because there is no more. So it says either there should be if there is no possible transition, then it's also not a part of the language, even if you are on a final stage. Because in your word, there are still more symbols that require transition. So what is, here is some more formal definition of formal finite automata. Okay. In simply, you can see finite automata like a graph, where the nodes representing different states, and we have the edges labeled with the language symbols A, B, B, whatever you have. However, to define this finite automata more formally, we use these 5 constructs, where Q is representing a finite set of states. The states in your automata machine must be finite, limited. It cannot be like infinite number of states. And then we have this sigma, which is for the alphabets, like you have A and B. And then we have this function, transition function. And the transition function is like, so for example, if I start from the 0 and if I get like letter A or B, where should I go next? So it's like a function that takes a state and also the symbol, and then returns the next transition from one state to another state. Okay, so we have a state and symbols, and then it leads to some new state. And then you also need some initial state in your automata, and you also need some set of final states. The only thing that you need to remember is that for each valid finite automata, there will be the starting stage or the initial state will be only one, but there can be more than one final states. We will see how we can get more than one final states. And also, we have 2 types of finite automatas. We have deterministics and we have a non-deterministics. Non-deterministics is when there is from one state with the letter A, if you have only one transition possible, if you can go only to one other state, then it's like a deterministic one. But if there are like more than one paths for the same state and the same symbols, then it's not non-deterministics. You get confused. Should I choose this path or should I choose this path? For example, if we see this automata, this is our starting symbol 0, and if I take the A as a symbol, I have 2 different paths here. The one path is this one, which leads me to the state 1. Another path is that leads me to the same state. So in this case, this is a finite automata, but this is not a deterministic one. This is a non-deterministic, because for one symbol, for a state, I have more than one path to move on. So, and this A or B, I have this regular expression, okay? And also, for example, if you get a regular expression, and if you have to define, I have to switch the mode. Good. So, if you have a regular expression, we have already seen regular expressions, which is A, R, B, and then A, B, B. And now our task is to define a finite automata, a state machine, for our regular expression, to check whether a string is a part of our regular expression or not. We say that in every automata you will have some initial state. So we call, let's say, this 0 is our initial state. From here, we get our starting point. The words should either start with the letter A or it can start with the letter B. So it means that from the initial state, I need paths for both A and B. Okay. If we don't have this star notation, okay, then we can do something like this, leading to a new state. But since we have a start, which means that A can come many number of times, and to represent this many number of times, then I have to define something like a cycle. Okay, and the simple way to define a cycle is, instead of going to another state, because we are in the cycle, we remain on the same state. So for the star, if you have a star or the multiplicity associated with some symbol, we use this looping edge. And this looping edge is being used for both A and B. So it means I also need, okay. So now from this automata, I covered this part. A can come, it could come 0 or more than once. And then afterward, what is the next? If you get the next, we need a path for the symbol A. We don't need from the initial state, okay. After some infinite number of A's and B's, there must be some path with the A that should lead to the end of the word, okay. So I take an A and then maybe go to a next stage. And then from this next stage, if I read B, it should take me to another, and then to the final stage, BB. Okay? Yes?
So how do we know that we're going to do
Yeah.
could do like A, and then A, B, B?
Yeah.
No. But
Yes.
you can.
Take some word that ends with, because the ending part is
Oh, so
this
it
one.
ends with ABB.
Yes.
Okay, so it can be A, B, B.
Yeah, it can be also. Because we say that B has a star. So star means it can even come 0. It can be also like A and A, B, B, B. It can be like, also be like B and A, B, B, B. We are only certain about the ending part.
Right.
We are not really certain about the starting part. The starting part could be, because it has a multiplicity, it can come or it may not come. And it can if it comes, it may comes many number of times. Yes.
Could it be AB, ABB? So AB, ABB.
You mean like the word over here?
Yeah, could it be AB and then ABB? Could that be a valid?
Yes.
Okay.
That will be a valid word, because we start from the A, we take A here, we take this part, and then we take B, we take this part, and then A, we take this part, B. Yeah. However, the question I was trying to explain was like, if it's a deterministic or if it's a non-deterministic, and how we can find that? We can find deterministic or non-deterministic if on every state you have only one possible path for a single symbol. So for example here, on the 1, if I take the symbol B, I have only one path, which is leading to the state B. And the same is true from 2 to here. But if you take 0, for the B it's fine, but for the A, I have two different paths. I have a path that keeps me on the same state, and I also have a path that moves me to the next state. So for such kind of finite automata machines, we call them, these are like non-deterministic ones. So we have different paths over here. However, the good thing is that we can, if you have a non-deterministic finite automata, we can transform them to something like more deterministic one. Because these things are very simple and easy to define. As you said that whenever you find a star, you keep a loop and then end ignition. But if you have to define deterministic ones, that might be a little bit more tricky one. Okay, so let's see if I go back to them. Yes. We have the same regular expression, A, R, B, and then we have star on them, both of them, and then ending with the ABB. And here I have defined a more deterministic ones. So we start with the letter, starting letter can be A or B. But if you see the previous one, in the previous one, the problem was for this A, we have two different paths. We have a path, this one that was leading to state 1, and then we have a path that was keeping us on the same state. However, if you see over here, from the 0, if I take A, I go to state 1, only one possible state. And then from the 1, if I have a letter B, I go to another state, but if I have a letter A again, I remain on the same. So that I can, by using this, I can accept A either once or more than once, or I can also omit this part. This one should be the other way around, maybe. No. Yeah, this arrow seems to be a problematic one. We have A, B, and A, B, B. A, B, B. Yeah, that's fine. Yes, you have a question.
You answered my question.
Okay. Okay.
Yeah.
Yes.
So the last picture, is it bad practice? Is it wrong to do it this way?
Yes, I will answer you in the maybe over here. I mean, whenever you have a DFA, non-deterministic one, you can always transform it to a deterministic one. But both have their own merits and demerits. And the merits and the demerits are more like when it's come to the complexity and the resource consumption. The non-deterministic one, they are easy to build. However, they require more. They require more time to solve the problems in terms of execution when you implement them. But on the other hand, if you see this deterministic one, they require more memory. They require more states. So, for example, here we only have like 4 states and only few transitions. But if you compare here, we have a lot of transitions, and to maintain all those transitions, so they are more memory consuming. However, the deterministic one, since you already have defined the paths, so they will be, if you implement them, they will be quite fast to execute. So they are more time efficient. But I mean, both are fine. They can be used to recognize a language. There is no problem in the language recognition. And so here we have some algorithm. So now we have seen this thing more like in a graphical form. But if you have to write a program, and so for that program, here we have some pseudocode, some algorithm defined over here. So we have like these 4. We need 4 basic things. We need something like an initial state. We need to know what is the from which state we should start, and also what are the final states. So in which state, if we end up, then it's fine. And then we also need some function, next character, and the next character should it should start from the first letter of our string, and then it should move on until the end of the string. Because the reason we are using this DFA or the finite automata is to recognize whether a string is a part of a language or not. Okay, and we do it by taking one symbols from different words and then moving to the next transition. And then you need also some function or method that takes two input parameters, state and a symbol, and then it should return the valid state where it should go. So Q is our initial state, and the C is the character that we get. So for example, if you have a string like A, B, B, that you given over there, A, B, B, okay? So this next character will give us the first character C, and we will have a loop that should continue until we are done with all the symbols. And then we call this function move. Q is the initial state now, and the C is the first character, and then it should return us the next state. And we should do it until we have done with all the characters. And after the loop, we should check which state we have achieved. And if that state is a part of the final state, then it means we have achieved our goal. Otherwise, it should not be possible. So for example, and here we have also, because this is more like a pseudocode and this is more like a Java switch case to use different transitions in your graph. So here is we have some summary of the things that we have learned so far about finite and deterministic and non-deterministic automata. Of course, I mean both are. If you have a DFA, you can. If you have a non-DFA, you can change it to a deterministic ones. But as I told you in the beginning, the one is more resource memory consuming, but the other one is more efficient or the fast. Okay. The next part we have is, so for example, if you have a regular expression and the task is that you want to change or you want to define a finite automata from that regular expression, so how can we do that? Take your regular expression and take a start sim to define two states and replace the whole your regular expression over on the edge over there. Okay. So, and then if you have a regular expression, and in that regular expression where you have a concatenation A and B, A, B, so you replace this with A and the followed by B. On the other hand, if you have an alternative form, then you use two different paths. And if you have this star thing, and for this multiplicity star notation, we have this epsilon rule. Don't ask me what is the logic of this one. The only thing is that it will give you the NFA, okay? And so it will be maybe more easy to see if we have an example over here again. We take the regular expression So our regular expression is given over here, A or B, and I think it's the same one, A, B, 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 that we have already done. However, we done it in the non-deterministic one, but now we want to do it deterministic ones, okay? And here, in this step, we know that for A, B, 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 we have this rule 2. We have shown already the rule 2, which says that if you have something concatenated, you can split it by adding a new state in the middle, okay? So we take this regular expression, we keep this part as it is, but we have defined this part by splitting them into 3 different edges. Now we are done with this part, so we can take this part. And for this part, we have a multiplicity, and for the multiplicity, we have a epsilon rule. So we apply the epsilon rule, and we get these things. It might be, if you see over here, so if you have this A, you start an E, you can think of this like an additional edge in your automata. And then you take an A and go back to E. And then another possibility is, since A can come many number of times, if you want many number of times, we can keep on circulating on this. And if you want it only once, you can directly go to the final state from here. Yep.
The last one, doesn't it say that it has to start with E?
No.
No?
E is like a help symbol. It's not a part of the language.
Okay.
E is like it's not a part of the symbols. So the symbol is only A or B. Even if you see here, I have added, by following the epsilon position, I have added the E. But we don't consider it as a part of the language.
But what does it represent?
As I told you, it's a rule. And to be honest, I don't really understand the basic theory behind them. It's given by some guy, smarter guy, to solve this puzzle of a star that can lead you to non-deterministic FAs. So instead of having a non-deterministic, you can have a more deterministic ones by applying this epsilon rule. So, and then we have solved, in this step, we have resolved this multiplicity notation. But then next we have this A or B, which is the only part left now. So, and on this step, we solve this by adding 2 alternative edges. Yes?
Is like the first part with the E there for representing that it could be nothing? Or
Yeah, it could be nothing, yes.
okay.
It's like an empty
Yeah, exactly. So
string.
if you had to have A or B, like it wasn't optional, but you had that one, you would start at 1 in this case, or like everything. Do you understand the question?
No.
Is it K if I like?
Yeah. Point it. More easy.
So in this case, if you have to have A or B, would this be zero state? So
If you want to have A or B.
yeah, you're not allowed to have nothing, but
Yeah.
So this would be zero state, or is this there for representing
No.
that it could be a nothing?
If you want 0, then you go from here to this one.
Yeah, exactly. But
Then you skip it.
yeah, but if say the regular expression would be that you have to have like not 0 or one
Yeah,
of those, but you have to have at least one of them.
Yeah.
See my point? Like if having a
If you want at least one of them, then you take this part.
yeah, exactly. So you start there. Instead.
Yeah.
Okay.
Ah.
That was my
Okay.
question.
Okay.
Thank you.
Yeah. Sometimes it's tricky to understand the question itself. Yeah. Is it clear? I mean, of course, it might be a little bit confusing if you try it for the first time. But if you, my advice is that you follow up after the lecture, and if you have questions, you can use the Moodle or even the Slack forum, whatever you prefer. So now, here we have seen that if you have a regular expression, and we can use by following these rules, we can transform a regular expression to a automata. But we can also do it the other way around. If you have finite automata, and you want, it might be the task that maybe in the exam that we give you automata, and then we ask to derive a regular expression from that automata. And for this, the technique we use it, we call it state elimination. And what it means by the state elimination, it means like if you have a automata where we know that we have like one initial state and we can have more than one final states, okay? And then we might have some middle states. So what you need to do is, if you remove the middle states and if you keep only the initial and the final states, you can get something like a regular expression. And how can we do that? So for example, here, if we have this one is the initial states and this one is the final states, it means that and here we have some symbols, A or B or whatever combination you have. If I remove this one, I can go directly from Qj to initial state to the final state, but then I have to combine these two. This is kind of opposite to this rule. So here we have AB, and I have, if R was like AB, I have split A, B into two different parts. But now, if I have A and B in two different edges and I want to combine them, then I have to remove this part. And if you see this now, it's more like AB. Okay? So let's say we have this automata which has the initial state Q0, and we have the final state, let's say Q3. Q0 is our initial state and Q3 is our final state. And then I have different transitions going on, and we want to achieve, we want to transform this finite automata into something like a regular expression. And the technique I am saying is state elimination technique. So you can start by removing the two states that we can remove in this case are Q2 and Q1. And you can start with removing any one of them. So for example, if we eliminate Q2, so it means if I am removing this Q2, and remember, when you remove the state, you don't need to remove the edges. You still have to maintain the connection between the other states. For example, the path from Q3 to Q0 is, if I go from Q3 to Q2, I can go to Q0. But if I remove this Q2, I have to add a path that can lead me to Q0. So I have now changed this into this edge. And since these two have symbols 1 and 1, so I have combined them together here, 1 and 1. You understand? And also, is there any other edge from Q3 associated with the Q2? Yes. From here you have to look at all the incoming and outgoing edges on the state that you are removing, and you have to connect with the other remaining states. So from on the Q2 we have one incoming edge and two outgoing edges, and for each incoming edge I have to connect with the outgoing edges. I have already connected this incoming edge to this outgoing edge by this 1, 1, but I also have to connect this 1, 1 with this outgoing edge 0, and this outgoing edge is leading to the state Q1. I already have a edge from Q3 to Q1 1, and to keep this connection I will add this 1, 0, because I always, if I have to use this path to go from Q3 to Q1, I have to start with the 1 and then followed by with the 0. So with the 1, with this path I have added an alternative symbol 1, 0. You understand? So I have now removed this state, but I still have this state left. So now the next step is to eliminate Q1, and when I eliminate this Q1, so it means that there is how many incoming edges? We have this one and this one. So, and we also have the remaining states will be Q0 and Q3, and we already have some connections between Q0 and Q3, so we need to maintain them. So for example, Q3, Q0, this one 1, 1 should always remain there, and this one from Q0 to Q3 1, it should also remain here with the 1. But then I have to combine these combinations, and how I can do that? By taking this path 0, and then I have a loop. Okay, so if I start from Q0, I can get, always will have to start with the 0, and then this 0 can come many number of times, so I will put star on this 0, and after that I can take this 0 to lead to the Q3, so I have put this 0 in the end. On the other hand, if I see this path from Q3 to itself, don't forget that part, because you have added the edge for this one, but you also have a Q3 to Q3 itself, and this path is starting from the 1 or 1, 0, so 1 or 1, 0, and then we have a 0 that can come many number of times, and then it ends with the 0. Okay, so I get this, and later on, to simplify this, I replace them with the letters U, V, and T. Is it understandable or too much complicated? Sorry? Somewhere in the between. Okay. And then if you take this U, and that's equivalent of this one, and then we have a V, and then we have also a T. However, if you see over here, now I put this U and then T, because after this U, T can come many number of times. So T can come many number of times, but also important part over here is when I go back from V, because Q0 is initial state, that's not a final state. Final state is Q3. So I can from V go back to 0 and come back again to U to this Q3 part. So I have to put V and U as well with the star. It looks a bit complicated, but I think if you try it with it carefully, it's not very complicated one. Yes.
I mean, like in the first example,
In the first example,
you had Q3 pointing to Q2, incoming to Q2, and then it was an outgoing to Q0. If you didn't have that outgoing arrow, can you still eliminate Q2 or?
it will be more easier if you come here and then point them.
You could eliminate Q2, how I understood it, because there was an outgoing to Q0.
Yeah.
Yeah, if you didn't have that outgoing,
Yes.
can you still eliminate Q2 or you can't?
Yeah, still we can eliminate, because that's what the state elimination says, that you start eliminating the state even if there is no, because there is still this one over here, or another outgoing edge.
And if you don't have that,
If you don't have that one,
either, can you still eliminate? Or
so if we don't have this one, no, then we can't.
we can't eliminate.
Then we can't.
So there has to be an outgoing.
And in that case, maybe because there was no outgoing edge, it would be more likely that that state will be more like a final state in your automata. What time we are now? Okay. We're almost coming to the end of the time, but we still have some things to cover up. But the good thing is that we have a lab hour, so if you're tired, I think I suggest that let's take 5 minutes break, not so long, and then we continue with the second part after the break. Okay? Yeah, it was 5 minutes.
Okay.
Precis, då är det
Hur det såg ut.
precis, för då kan det fortfarande gå runt. Eller?
Ja, precis. För den går tillbaka.
Ja.
Ja.
Då kommer du inte på hur de var.
Nej, men jag ville se så att man får ihop den och bara ihop alla. 0, 1, 0, 2.
Okay. So next we have so far we have been working mainly with the regular expressions, and in the beginning I told you that we have like two different ways to define the constructs for our languages, like regular expressions, and but the problem with the regular expression is that we can only define a limited constructs using the regular expressions, and they are usually used to define identifiers and the keywords in a language. But there are more advanced constructs that are needed, and to support those definition for those constructs, we have the notations in the form of this context-free grammar. It's quite similar to the regular expression, but not exactly the same. In the context-free grammars, like in the regular expression, we have symbols. Here we have symbols as well, and but we divide the symbols into two different types. We have like terminals and non-terminals. So the terminal means that the basic alphabets, and then we will also have a helping symbol. So for example, if we have a language, here we have a context-free grammar, and we have like two production rules. The first rule says like A, and this A can be replaced with the A and capital A and the small a. And here this capital A is a non-terminal. It's like a helping symbols, and this A is a terminal, like the alphabet. And then I have another rule which says that whenever you have an A, it can be replaced with the B. Okay, so from this language, the basic rule we have is whenever you have A, it can be replaced by B. So from this rule, we can get the word that contains only one B. But if I take the other rule, A leads to AA, and in this rule, if I know that we have A which can be replaced by B, and if I replace this A with this B, I get another word, BA. Again, if I take here, I replace this A with the B, but I can also replace this A with this whole rule again, AA, and then I replace this A with itself, AA, and I get PA. Okay, so in this way, so we get infinite. So this is basically same like we have a regular expression like this, starting with the letter B, and then you can have A 0 or more than one times. So in the context-free grammars, in the regular expression we have a symbols, and then we have a basic constructs. In the context-free grammar, we have a production rules in the form of these notations, help symbols and alphabets. And again, we can write these rules as a separate rules, or we can also combine them using the R notations, because this says like A can be either AA or A can be AB. Okay, so this can be written also like using the R operator. Now here we have another grammar in this time, and of course with this help symbols A, you can use any letter like A, B, C, whatever you want to use. Here we have a context-free grammar which says the B, and then we have a small parenthesis, and then BB, and then the empty string. So these are like three different rules. Okay, and using this grammar, what we can get is that we can get a language of balanced parentheses. Often we have a case in our programming where we have to check if you have open small brackets or the curly bracket or parentheses, do you have closed it or not? And if you have to make sure that whenever you open a bracket, there must be a closing bracket. So it means that you should have a balanced. You should have to something that should be checking the balanced parentheses. And so from this regular expression, the context-free grammar, we get this language. Okay, it can be, there might be that you don't use any parentheses at all, and there might be that you use it only once, or maybe the nested blocks. Okay, so let me switch to the whiteboard mode. Oops. So the grammar we have is basically B, okay, and we also BB, and we can call them like this is rule number 1, this is rule number 2, and this is rule number 3. And if you have to check, for example, from that example on the slide, if I take the last example where you have nested and then you have another parenthesis. If you have, we have to check that whether this one is okay according to this context-free grammar or not. If I take rule number 2, the rule number 2 says BB. Okay. So now what I am doing is I am taking a grammar and I am deriving this sequence of parentheses or strings from this grammar. I take this rule number 2 and I write BB. Now I want to achieve this thing, and if I replace this B with the rule number 1, I will get here I have replaced this B with the rule number 1. Now on the next step, I replace this B again with the rule number 1. And here on the next step, I replace this B with the rule number 3, which is empty string. So I get, so I'm done with this part, but I still have this part. And for this part, if I write it again over here, now if I replace this B with the rule 1, I will get this B. And now if I replace this B with the rule number 3, I get that. Okay, that was the more complicated example. So it means that using this grammar over here, we can get all the different possible combinations of balanced parentheses. Similarly, if you see your programming languages, as I showed you in the beginning, the Java language specification, you often have this different statements are the part of your language defined using the context-free grammars. So for example, you can have a statement list, and here this statement list is like a symbol B, and then you can have a state B again, and then statement R, just only a statement. So this is like A followed by A and then R, B. And then you can replace this, further define this statement with the while statement, if statement, for statement, and you carry on. So in general, context-free grammars, they are more expressive and more powerful than the regular expressions. So whatever you can define using a regular expression can also be defined using a context-free grammars. But on the opposite way, it doesn't work. So if you can define something in a context-free grammar language, then there is no guarantee that that language can also be defined using a regular expression, because regular expressions have some certain limitations we will see in a short while. So we already have defined a regular expression for a language where the length of the string was even. Now using the same alphabets of two symbols A and B, if I ask you to define a context-free grammar using the syntax of a context-free grammar, we already seen that we identified the basic cases AA, AB, BA, and BB. And then we put star notation so that it can be repeated more than once. And if I have to define this in the form of context-free grammar, if you put A again with everyone, it means that this one can be replaced with this part or this part or this part. So if you have to use, if you have a word which is composed of 4 A's, let's say 4 A's, the length is even. So I took this part A, and on the next step I replace this A with itself again, and in the last part, when I want to stop, I take the empty string. So it's important that for such type of example, don't forget the empty string, because if you don't put the empty string, there will be no end of the story. You will always keep on adding an A. However, now we have a new exercise, and for that exercise, it says that write a context-free grammar describing a language which is composed of two symbols A and B, and it should start with the A but followed by the same number of B's. The words in that language must start with the A, and then it should followed by the same number of B's. So for example, if you have one A at the start, then there must be one B at the end. If you have two A's at the start, so then you should have two B's in the end. Can you press the board? So it means that if you have one A at the start, it means that you should have one B. If you have two A's, you must have two B's in the end. If you have so on. It cannot be like this, like A, B, B, because this is wrong. You have a 1A, but you have a 2 B's. Okay. Can you come up? Can you help me to define this language using the context-free grammar? And the alphabets we have are the same, like A and. What is the base case over here? And also the important part in that definition is that the number of A's and B's must be greater than zeros. So at least one. So at least one means the base case will be this one. So we at least there must be at least one A and one B. So it means that the base case for this is this one, AB. And then how can we define a rule where we can have the same number of the B's should the A should be followed always should be followed by the same number of B's. Sorry. If it's small a here or yeah. B again? You mean like this?
No,
Big A.
not like that.
Okay, we can try. I mean, okay. So if I take like this, let's say, can you try? How can I drive this word with your? What should I start with? If I took like this, A, and then I can replace this with AB, with this one, and then B, but I still have an A.
AB again.
Sorry?
AB.
A, B, B. So I replace this with the. Then it's no. A should not be in the middle. A should always be in the start. Because it says, if you see over here, A must be at the start, and then it's followed by B, and the number of B's should be the same as the number of A's. Because this is
By removing the last
by removing,
ace,
yes,
exactly, then it will always be added in the middle.
then it will always be added in the middle. Okay, let's try. So if I take like this and I say that this is rule 1 and this is rule 2, okay?
No.
Sorry?
No.
Okay. So if I try for this one, A, what should I replace with this one?
AB.
To get this word. Let's take first this one first. If I have to derive this word, I take A and replace this one with this one. I get this word. That's fine. If I take this one, I take A, B, and then I replace itself with the same. Okay, and then one more time. What is the problem now? I somehow need to get
Empty.
okay. So you was right by putting this in the middle, but then you also need something to stop it. Now we have done this one. If I ask you to give me a regular expression for this, can you give a regular expression? How can we get a regular expression? Now I will answer your question. That you said that why should we use DFA and the state elimination? Because if you have a language, sometimes it's very tricky to define a language by directly going to the regular expression. Instead, if you can define a DFA or a finite automata, and then once you are done with the finite automata, then you can use the state elimination technique to get a regular expression. So for example, if I want to define automata for this language, okay, we start with the initial state, which is 0, and I say that whenever we get a letter A, it must be followed by B. So it must be followed by B, and in this case I can say that 0 is both my initial and final state. So from this I get this word, okay, AB. But then I have this one, AB. Maybe I can solve it by adding another one. However, this is never going to an end.
No.
So this shows that this language cannot be defined using a regular expression. And this is just one example, and there are other constructs that we cannot define in the regular expressions. Also, the balancing parenthesis example, that can also be not defined using regular expressions. So that's why we need, for some constructs, we need context-free grammar. So there are different language elements that cannot be done using regular expressions. So here, we have the solution, the answer for that, A, B, and AB. Okay. No? Yeah. Yeah, I was wrong on that part, because if you see, we can put this AB instead of, when we want to stop, we can put this AB and go to the ending case, even without using the empty string. So more formally, as we said that regular expression, we have some symbols, constructs, and the same for the finite automata. Similarly, for the context-free grammar, we have terminals, non-terminals, we have production rules, and we have starting symbols. Okay, the production rules are like this that we define, and terminals are our alphabets, basic alphabet like A and B, and these non-terminals, these are our helping symbols A, B, that we keep on replacing every time over here. Like for example, here A and C, these are terminals, and the terminals we write often in small letters, and all other characters like A, B, and D, they are like help symbols, and we call them also non-terminals because they are not the final in our language. Okay, and then we have the production rules, and we also have some starting symbol in our context-free grammar. Here is another example. We have for example, we want to define a language for this kind of constructs for the arithmetic operations, plus and multiplication, and that could also involve small parentheses. Okay, so the basic symbols, if you see all those examples, so the alphabets we have for this, the terminals, we have A, B, C, and then we have a plus and multiplication, and we also have this opening and closing parentheses as our symbols. These are the part of our alphabets or terminals. And then we have some non-terminals, which is E, and then we have a starting symbol as well, which is again the E itself. And now, if we define, if we want to define the production rules to derive this language, we have some basic cases, and in this case, the basic cases are A and B and C for the symbols that we have, and then we have this production rule, and this production rule. And how can we use these production rules to derive something? For example, here A plus B multiplied by C. We have these 1, 2, 3, 4 different production rules. The first production rule says that E can be replaced by either an A or B or C, which are our terminals, symbols. And the second rule says that small parenthesis and in the middle the non-terminal symbol, the helping symbol E again. And then we have a E plus E, and then we have a E multiplied by E. To show that A plus B multiplied by C can be defined by this grammar, if we can start with by taking any of these rules. Okay, if I take this rule, I cannot move further. I will just, from this rule, I can get either A or B or C. I cannot get anything else. So this is not a good choice to produce something like this. To produce something like this, you should either pick this one or this production rule that involves plus and multiplication. If I take rule number 3, E plus E, and then on the next step, I can take rule 1 and replace this E with this A, and I get A plus E. The next, this E, and we replace it with this one. We get E multiplied by E again. And here, I think we already are close to get something which is the final one. And in this rule, we replace this E with the B and this E with the C. If you see that in this derivation, I was always replacing something on the left side. And this kind of derivation where you replace the symbols on the left, that's simply called leftmost derivation. But it could also be done from the right side, where you always replace the symbols from the right side, which we call a rightmost derivation. So, and this derivation can also be represented in a tree form. And the tree that we get from this derivation, we call it a parsing tree. That is often used by the compiler to check whether the strings that you have, they are valid strings or not. Okay? So again, we have this derivation starting from A multiplied by E. We take E and we represent this part E multiplied by E as here. And on the next step, if you are following leftmost derivation, you can replace this part. But if you are following rightmost derivation part, then you will always be replacing the right part. So here I replace this E with an identifier. And identifier in this case are the basic symbols A and B or C. Okay, so the letter here we have a C, so I replace, you can see this ID as a C. And then once you are done with this one, you can then take this E plus and replace this E with E plus E. And then you can have ID for both of them. Yes?
Is it just a matter of taste if you use leftmost or
Yeah.
rightmost, or does it matter?
No, doesn't really matter. These are the both. I don't know there is any difference between two of them. So you can use any of them. Okay. So we have an exercise over here that says that, but I think we have already done this one. It's you have this grammar rules B and B, and it asks you to show whether this is a part of this formal language or not. So you can, if you have to show this one, if you start with this one and then you keep on continuing replacing, you will get up with the final result like this. And similarly, if you have a grammar this and you want to show this one, you can start with one of the rules with the plus or multiplication, and then you can get to the end result over there. And here we just have a parsing tree. This one is for this derivation, and this one is for the other derivation. So basically, if there comes a question that you have been given with the grammar rules or the derivation, and somebody could ask you to define a parser tree, so what you need to do is you always start with the starting symbol. If your starting symbol is E, you put it as a root node in your tree. And then you take the next rule. For example, here we have the next rule, E, and then the next thing that is on the right side of your start symbol, you add it as a child nodes. So here we have a E multiplied by E, so we add them as a child nodes to our root node. A common problem in the language definition is ambiguous grammar. And a grammar is, what does it mean, that the ambiguous grammar? It means that because as I told you, when you are writing a language, and if you have written a language and you want to compile it and execute the instructions given on them, your computer first needs to compile and interpret and validate whether your instructions are correct one or not. And during that, you are often using this recognition part that we have done manually on the whiteboard, whether the strings should start with the A, should be, either you should have a semicolon, starting brackets, missing brackets, so things like that. And these are often done by the different compilers by generating these derivations using tree data structures. And for the tree data structures, you often use the term like a parser tree, okay? And in the parser tree, sometimes there might be that your grammar can produce more than one trees. And if it is possible, either using leftmost derivation or rightmost derivation, if for your grammar, for a string, if we can get two different parser trees, then it indicates that you have an ambiguous grammar. And in case of ambiguous grammar, your compiler might get confused. So for example, here we have A plus B multiplied by C, and we can have two different parser tree for this derivation. But the good thing is, whenever you have an ambiguous grammar, you can work on that and make it unambiguous. But how can you make it unambiguous? Only thing is that you have to redefine your grammars. And how can you check out if you have an ambiguous grammar or not? By defining the parser trees for one or maybe different strings that are the part of your language. So, for example, here we have defined the grammar rules for that, but I mean this one, E, A, B, C, E, E plus E, and E multiplied by E. But the problem with this grammar is that it leads to ambiguous, it leads to different parser trees, which means that this is an ambiguous grammar. And if you have to redefine it in using these rules, now whatever derivation you use, you will always get a same parser tree. So, for example, if you have to show this one, A plus B multiplied by C, we're starting with this rule, E plus T, and then if you are using the rightmost derivation, you take this T and replace this T with this production rule, T multiplied by F. Again, we are using the rightmost derivation, I take F and I use this rule and I replace F with the ID C in this case. The next, I have a T and I take this T and take again T, this alternative part, and replace it with the F. Now going back to E, and for the E we have this rule, terminal E leads to terminal T, and replace it. So if by using this grammar, whatever the string that you have, you will always end up with the same parser tree. To give you an example of how this ambiguous grammar can be a complicated problem, one common example is this dangling else statement. And the dangling else statement is like, for example, we have this grammar defined for the if statement, and here we have two tree-like if statements. Can you tell me this else, is it associated with this if or with this if? And the same like here. I mean, of course, if you look at visually, it seems like this else is a part of this if. But if you look at like this, it looks like this else is a part of this if. So this is like because of the ambiguous grammar. If you make it very clear, for example, in the Java, it clearly defines that doesn't matter if you have intended it in what way, the else will always be associated with the closest inner if. So it means that in both cases, even if you have written it like this or written it like this, Java will connect this else with the inner if part. So now we have seen most of the parts about context-free grammars and also with the regular expressions. And as I told you in the beginning, I mean, both we use to define different constructs in our languages. The difference between the two is regular expression is a subset of context-free grammar. Whatever you can define using the regular expression can also be done using a context-free grammar, but not the other way around. So for example, we already seen the example of a language comprising strings starting with the A's followed by the same number of B's. That can be defined, that cannot be defined with the regular expression. And also, but on the other hand, the common approach is, because the regular expression, they are easy to define and understand. So the basic constructs like keywords and identifiers, they are often described using regular expressions. And when it comes to the more complicated constructs, then the good choice is to use the context-free grammar. The last part of today's longer lecture, that's more kind of a theoretical. It's not really important for you to understand. So when it comes to the languages, this guy, Noam Chomsky, is more like a linguistics American professor. He has defined the 4 different classifications of the languages, where the regular languages, if you see on the top, they are like most simplest one. And the natural languages that we speak, they are like kind of more complicated one and more advanced ones. And the context-free grammar, they are kind of in the middle. But you don't really need to maybe bother about that. So it's like defining language using the regular expression is more in terms, as a computer scientist, if you see for yourself, these are more simple and easy to work with. But we can only define limited constructs with them. On the other hand, with the natural languages, for us, they are also, easy to understand, but for the computers, defining something that is close to natural languages itself is a challenge. So that's why often we end up with something with the context-free grammars or context-sensitive grammars. Okay? So that brings the end of today's lecture. And but before that, if you have any questions, you can ask now. Sherlos, I think I don't know if he has announced it on the page or not, because he told me that he has some problems, so he might be not coming today for the tutoring session. But I will be here for at least for some minutes. So if you have questions, of course we can take now or even after the lecture. And also he told me that he will be available on Skype or Slack. So even if you need some help now from him, so he should be available. Okay. Okay. So thank you very much.
Do you have any?
Yeah, I just need to stop this and then.